5, 4, 3, 2, 1.
Hi, my name is James Weatherly. I'm a mechanical engineering student here at Clemson University, and I'm graduating this May, so I'd like to apply for your fall internship position. In this video, I'd like to tell you a little bit about the robot team that I've been leading this past year. We're competing in the 2017 ASME Student Design Competition, which is based on the Olympics, so our robot must compete in 5 events. So, beginning last fall, I led a team of 13 students through the entire design phase to come up with our final design, and this semester we're building it. I spent an average of 20 hours per week working on this robot, as well as leading the team and coming up with the overall architecture for the robot. So I'd like to show you some pictures and videos about how the contributions I've made have led us to a design that I think could win us the entire competition. I present to you our robot. It looks a little boxy, but that's because there are sizing requirements which dictate it must fit into a 50 centimeter sizing cube. As I mentioned, there are 5 events: the sprint, the climb, the lift, the throw, and the hit. Given some of these events were similar, the first decision I made as team leader was to make 3 groups within our team: the locomotion group, the lift group, and the launch group. I played a large role in the design of all the systems, but I'll focus on the locomotion system and the lift system. The locomotion design needed to be able to climb up and down a series of 3 steps as fast as possible. We chose a tank tread system where the back arms lock into place, and the front arms have full range of motion to allow it to lift itself up onto the steps. I chose this geometry to allow for the robot to climb directly up the steps, regardless of the step size and length that was chosen at the competition. I specifically designed the linkage system for the back arms to lock into place. This allows for the greatest forces to be transferred through the arms instead of an actuator. We are currently still working out the kinks in our wooden prototypes before we make the final design out of aluminum. Now, back to the lift system. The score for the lift event is calculated by multiplying the mass of the weight lifted times the height it is lifted. The challenge with this system was creating a system that was compact yet strong. After several designs and multiple tests, I decided on a forklift design which takes advantage of drawer slides. I expect to be able to lift 100 pounds, possibly more, nearly 7 feet in the air. The system has over 200 machine parts, which means I'm in the machine shop quite a bit. This system has some tight tolerances, which has required my experience with geometric dimensioning and tolerancing. Quick side note, I have the definition of a hands-on background. Between all of the mopeds, jet skis, motorcycles, trucks, and co-op projects that I've worked on, I've accumulated thousands of hours of experience making things work. Now, back to the robot. I'm simultaneously leading the construction of 3 systems of our robot while taking 17 hours of classes, so I'm regularly working 80 to 90 hours a week to make sure that I am successful. I'm extremely motivated to bring Clemson its first ASME Student Design Championship. Though the competition isn't until April of this year, I would bet anything that my team will place first. As you can see, I poured a tremendous amount of effort into the robot team because I see it as my SpaceX application, that I can pour time and effort into a project and drive it to success. But why do I want to work at SpaceX? Well, on December 21st, 2015, I watched the first orbital class rocket being landed back on Earth, and it changed my life. It was my first webcast, and I knew that I wanted to work at a company that was doing things like that. I wanted to work at SpaceX. So this was a short video, so I look forward to talking to you more about my background and my experiences, and I look forward to a future